Hello and welcome. This video is all about test benches in VHDL. So this is the second part of the video series I'm making on counters. And for this, I will focus on test benches. Now, test benches are not unique to counters in any way, not by any stretch. However, when programming with VHDL, we often use test benches. Now, what is a test bench? A test bench is just like if you had if you were in a laboratory and you fabricated an entity, a piece of item, whatever that item is. If you fabricated that particular item, what you might want to do is to bring this item and then put it on a workbench, or if you want on a test bench. And what you're going to do is connect a bunch of inputs to it, and you might want to measure what are the various outputs that come out of it. So you place your entity on a test bench, connect some inputs to it, monitor the outputs. That way you can tell if this component is working very well or if it has failed the test. Now, this is the same thing that we do in VHDL, and a test bench is simply a piece of VHDL code that is effectively a workbench in which or on which we can place our entity as a component. We could connect a number of entities together. Let's say we had more than just one component. We have them interconnected in a certain way, and then we supply our input and we monitor the outputs from maybe the final entity, or maybe from each one of the entities. We monitor all the outputs as the case may be. Maybe you want to supply inputs to different ports of different entities. Point is, you can supply inputs anyway. You can monitor the outputs in any way. So a test bench is simply a piece of VHDL code which you can use to do this. So to talk about test benches, we'll go ahead and talk about the T flip-flop that we developed in the last class. In the last class, we came up with this, we drew this model of a T flip-flop. We know how T flip-flop work. You have a clock signal that comes in, and the output should flip as long as whenever there's an active clock transition, your output will flip or will toggle from one state to the other. We also mentioned we could have asynchronous inputs, for example, set and clear. So let's go ahead and test this. So let's do our design. Remember, your planning phase is always the most important phase, or at least one of the very most important phases of your VHDL design. So we're going to have a test bench. Let's give a test bench a name. So we're going to call it TB my TFF. Okay, my TFF was the name of the entity in the last video, so let's as well just use that. So TB my TFF, does it have to start with the name TB? No. Is TB a keyword? No. I chose to call it that. So you could call your test bench whatever it is you want. The test bench is an entity. Remember, every object in VHDL is an entity. So the test bench is an entity, but then we're going to place in the entity we want to test. So in this case, we have just one entity we want to test, which is our T flip-flop. So I'm going to as well put it in here. What are the ports the T flip-flop has? It has one input port, that is the clock signal. It has one output port, which is our Q. But it also has an asynchronous set and an asynchronous clear. These are sometimes also called preset and reset, or preset and clear, but then I'll call them set and clear. We activate those are active low. So what we want to do is supply different inputs to this my TFF. So this is my TFF. I'll call it my TFF1. Okay, so maybe I should try to rewrite that so that it goes in there properly. So I'll call this my TFF1. Now, the reason I'm calling it my TFF1 is that I could have decided to place many of these, or several, or more than one my TFF inside this test bench. I could have decided to supply different inputs to each one of these components, or I could have decided to interconnect them. We will actually interconnect them in a later video, probably in the very next video. But we're going to interconnect them to form a counter of sorts. And then while they're interconnected, we'll test that entire connection. But in the meantime, let's just test this single component, and I'll call it my TFF. So to supply inputs and monitor the outputs, we're going to need to send in signals. Okay, so we can send in inputs and monitor the outputs through signals. What's a signal? A signal is a wire in VHDL. Okay, so we need signals. So I'm going to connect a signal to this. I'm going to connect a signal to this asynchronous input and another signal to this asynchronous input. Then I'm going to connect a signal to this here. Now, one thing I need to specify, a test bench in VHDL is the only entity that has no ports, no input ports, no output port. So notice this entity does not have any ports on the outside of it. Everything happens within this test bench. It has no ports. It is not meant to interact with the world in any way. It simply is an entity in itself that we created only to bring in something else into it to test that something else that we are bringing into it. So let's give names to these signals. Because the signal is going to the clock, I'll simply call it S_clock. And because this signal is going to the clear, I'll call it S_CLR. I think we call this CLRN, so I'll call it SCLRN. Again, you could call it whatever it is you want. The set and the signal name does not have to be related to the port name in any way. You can call it anything you want, but I like to call it this way so that once I see the name of the signal, I have an idea where it is, what it's supposed to be connected to, and I'm less likely to make a mistake. Then our output will be connected to S_Q. I think that's it for the planning phase. We know all the various things we need. We need to have an entity called TB_my_TFF. I need to have bring in a component, my TFF, into that entity. I need to have 4 signals. Each one of they have S_clock, S_set_n, S_clear_n, and SQ. Maybe one thing I should also specify is that I want to initialize my clock to 0. Because it is triggered by a positive going transition, I will initialize it to 0. So whenever I go to 1, that will clock it instantly. My Q, I will also initialize to 0. You can initialize to whatever it is you want. Because my set and my clear signals are active low, I will initialize each one of them to 1. I'm initializing to 1 so that originally this device will not be cleared and will not be set initially. Okay, that's to start out. I can now decide when I want to supply a signal, an active signal to set or to clear as I want. So this is my architecture of the T flip-flop. Let's get into quarters and let's write our program. Okay, so this is quarters, and this is my TFF entity that we created in the last video. Now what I want to do next is to test this entity by creating a test bench. Now I could go ahead and create a test bed entity inside this file, but I won't do so because it's well, it's sometimes a good idea to just separate things. And remember, a test bench has no ports, okay? Has no input port and no output port. If that's the case, then it means that we could actually we are not a particular test bench. We could have several architectures of a single test bench, and each architecture could be used to test a different entity or a different arrangement of components. So you could just have one entity declaration and several architectures in there. So just run a particular architecture you are interested in and test that architecture. Now to simulate or to go ahead and simulate a test bench in VHDL, we want to use what is called ModelSim. When you install Quarters, you also installed ModelSim in a great likelihood. So there are 2 things we're going to need to do. If the first one, if you've not done it before, you're going to have to do it, but you have to do this just once. When you install Quarters, you do this just once. Go to Tools, go to Options, and go to EDA Tools. Tools, Options, EDA Tools. Now you want to select the part, whatever simulation tool you're going to use for simulation of VHDL code to run your test bench. Whatever it is you're going to use, you're going to specify that in here. In our case, ModelSim Altera is what I have installed, and for my students here at the university, ModelSim Altera is what you're going to have installed. So if we click on the 3 dots over here, we can now go to the Intel FPGA Lite, which is where Quarters was installed. I have version 20.1 installed. Under that, you see ModelSim ASE. Okay, so ModelSim ASE is what we want to go into. Inside that folder, I'm on a Windows machine, so I look for Win32ALOEM. Double click on that and then select that folder. So the folder we selected is Win32ALOEM, which is inside ModelSim ASE, which is inside the 20.1, that's Quarters version that you have installed. So once you do that, okay, first thing done. Second thing we need to do, when I created this project, if you remember, let me go to settings. When I got to EDA tools settings, for simulation, I left everything as default. I had none for design entry, none for simulation, none for board level timing and all of that. Now, because I want to do a simulation now, I need to specify what tool I want to use for simulation. So let me do that again. Right click on this device over here, go to settings, or just press Ctrl Shift EE. You probably will be under general. You need to navigate to EDA tool settings, then go to simulation. Remember, ModelSim Altera is what I have installed. So ModelSim Altera, I'm using VHDL, so I specify VHDL in here. Okay, and we're done. So to run ModelSim or ModelSim, just come to your tools, run simulation tool, RTL simulation. Once you say RTL simulation, then it simply goes to, remember, tool options. You specified what your simulator is, and by default, and then for this particular project, you specified what your simulator is. So it just simply decides to run whatever simulator you have specified in this under your settings over here. Okay, so whatever tool you have specified on over there. So ModelSim is starting up. I should also mention that you do not have to start ModelSim from within Quartz. You could have just gone to your start menu. You could have just gone to your start menu and then look for ModelSim and have that and just simply run it from there. So okay, here we have ModelSim, and ModelSim has this is ModelSim over here. So you're interested in creating and sorry, I just want to resize this. I don't want to make it, I don't want to maximize, I don't want to fill up the screen with this. Okay, so I just keep it like this. Maybe I'll maximize it later. Now, we want to create another file. I could create this in Quartz, or I could create it here in ModelSim. So let's go ahead and create it in the ModelSim. Now, if all you're doing is simulating, you want to create an entity and you want to simulate it in a test bench, in all fairness, you do not have to open up Quartz at all. You don't have to create a Quartz project. You don't have to specify what FPGA you're going to be you're trying to program, because you don't plan to program it anyway. You're just creating a VHDL file. So you could create a VHDL file, compile the VHDL file here in ModelSim. You could create a test bench file, compile the test bench file here in ModelSim, and run your simulation. That will work perfectly well. So I'm going to come here and create a new, a new source. The new source is VHDL, is a VHDL source. So I'm going to create a new source, and here we have a text editor in which we could type in our code. So I'll go ahead and type in my code. Library IEEE. I'm going to use IEEE dot standard logic 1164 dot all. 1164 dot all. Okay, 1164 dot all. Now let's go ahead and create our entity. Entity tb underscore my underscore tff is end entity tb underscore my underscore tff. Remember, it has no port, so that is our entire entity declaration for this test bench. Architecture, you could call it anything, but I'll call it test underscore my tff. Okay, so I just make that a little larger so we can see it better. So test underscore my tff of tb underscore my tff is begin and architecture. Now you could actually decide to dock or undock this. I'm going to undock it just so that I can make it even larger so that we can see this as well as possible. Okay, sorry about that. Resize, good. Okay, end architecture test tests underscore my tff is, oh no, sorry, that's the end statement. Okay, so end architecture. Now, remember what we have. We have a number of signals in here. So set underscore n, and so s set n clear n. Let's start with those two. Signal s underscore set n and s underscore clear n. Both are of type standard logic, and I will initialize both of these to 1. Then I have two other signals, set s underscore clk and s underscore q, and these are also of type standard logic, and I will initialize these to 0. Now, one more thing we have not done, we need to bring in our entity, bring in our components. Okay, so we need to bring in our components. Sorry, I pressed Ctrl S, so it's going to ask me to save this somewhere. Now, I could save this anywhere, but what I'm going to do is I'm going to save it inside the project we're working with. That's the TFF. We had a file called TFF, so I'm going to save it in here. So tb underscore my underscore TFF. Now, okay, so tb underscore my TFF, I'll just leave it at that. Sorry, let me do, I want to confirm that I saved it with the right extension. Yes, I did. It's a VHDL file. Okay, let me see. .vhd. I think I need to type in the .vhd. Yes, .vhd. I need to put that in there. It saved it initially without the .vhd, and that might end up being a problem in the sense that I might not find it when I need it. Now, I'll go ahead and open the other file that we're working with. That is the TFF file. I'll just open that here. The reason is that I want to copy out this code. Let's make this a little larger. So I want to copy out this code over here and just take that as my entity. Now, is it possible for me to use work dot? Now, okay, so let me just get to that point, and then I'll address what I was about to say. Components. So I'm bringing this as a component, so we're not going to specify it as entity. Okay, so component. Now we're going to have to do a port mapping in here. To do a port mapping, I decided that I want to call it my underscore TFF1. Okay, so the reason why I gave it that name is I'll use it in the port mapping here. The component name is my underscore TFF port map, and we're going to put in our mapping in here. Now, instead of doing it this way, could I, instead of bringing in this component in here and now just using this over here, couldn't I just have used work.myTFF and use it that way? Well, Quartus is happy with that. ModelSim, you need to figure out how to use that command within ModelSim, and it doesn't always work exactly the way it works in Quartus. So I won't go through that trouble right now. I'll just simply have my declaration this way because this works. Okay, so in our component, we want to map CLK in the component to S underscore CLK. We want to map Q to S underscore Q. We want to map set N to S underscore set N. And just to show you that in case you do not know that we could do our port mapping in this way, let me actually do it differently. Let me put this on separate lines. Now, in VHDL, semicolon is used to delimit, is used to specify the end of a command, so that if you put things on separate lines, it does not clear n. It does not mean that VHDL does not consider that, the compiler does not consider that as the end of a command. It waits for the semicolon. A comma simply tells you that, well, we're still going on, but it waits for the semicolon before it takes that as a complete command. Clear N. So we can go ahead and define our port mapping this way. Sometimes, particularly when you have several ports, it's easier to put this in a column than to have all of them in a single row. And sometimes it's a good idea to, or generally it's a good idea to make things align. When they do align, it makes your code a little easier to read, and you're able to tell what is what. So it's generally a good idea to to align things. And so one issue you might have is when you're using tab, it might be aligned in Quartus. You go to a different text editor, for instance, what you have in ModelSim, and suddenly they're not aligned. So using spacebar sometimes generally makes it aligned across different programs. But that's kind of by the way. So we have our port mapping. Port mapping has been done. The only thing that is left to do right now is to supply stimulus signals to our clock, our set N, and our clear N. Once we supply those stimulus signals, we can monitor our Q. Okay, we can monitor the Q. Control S, I've saved. And let's go down, and now we want to supply signals. Now, what we're going to do is to supply a signal, then we'll supply another signal, and then we'll supply another signal, and then after some time, we'll supply another signal, after some time, supply another signal. In other words, all I'm trying to say is what we're going to do is a process. Okay? We're doing things sequentially, supplying one signal, and then another signal, and then another signal. So let me use this as a kind of a formal introduction to processes. Processes in VHDL are used for specifying sequential code that you want to happen one at a time. You want the first to happen before the second, and that should happen before the third, and that should happen before the fourth. So for a process, typically you will have a sensitivity list. In other words, run this process whenever whatever is in this sensitivity list changes. So for example, if I had said process underscore SCLK, then what is going to happen is that this process will run only when there is a change in SCLK. If there is no change in SCLK, this process does not run. But because this is a test bench, I will not specify a sensitivity list. This is probably about the only time we do not specify a sensitivity list. And process. Okay, so this is probably about the only time you don't specify a sensitivity list, and this is when you're working in a test bench. So what do we want to do first of all? Now, there's some, when you're working in a test bench, you could use a wait command. So for instance, wait for 2 nanoseconds. Okay, we could say wait for 2 nanoseconds. VHDL understands NS as nanoseconds, so you don't need to define that anywhere. 2, well, you know what 2 is. So you could tell it to wait for 2 nanoseconds. And one more thing I should specify about processes. Okay, let's write a few more lines of code, and then we'll talk about what else to specify about processes. Excuse me. So the first thing we're going to do is let's supply clock a couple of times. SCLK will be equal to not S underscore CLK. Okay, so I'm going to do this a couple of times. In other words, I'm going to change the state of the clock a couple of times. So clock, I'll make it high, then I'll make it low, then I'll make it high, then I'll make it low. So I could take this code and I could copy these 2 lines of code and I could paste them a couple of times. But this is actually a waste of time stroke resources if you want. Do you really want to be typing things this way? There's a better way we could do it. We'll do that shortly. Let's wait for 2 nanoseconds, and then let us now change our, let's see, how many cycles do we have here? This is 1 complete cycle. This is a 2nd complete cycle. This is a 3rd complete cycle. Okay, so if this started, so let's now activate, let's have my S underscore clear, and I'm going to assign an active signal to it. Remember, it is active low, so I'll make that active. Then I'll wait for 5 nanoseconds in this case, just so that, or let's make it 3 nanoseconds. Let's not make it too long. 3 nanoseconds so that it is different from the others. I'll make it 4 in this case, just so that, yeah, we see that nothing happens during that case. In fact, while that is there, let me as well change the value of the clock. I'm going to change the value of the clock just to see, does this affect the component in any way? And let me do one more thing here, and let me mention the other thing I wanted to specify about processes. When you have a process like this, I said this statement will run before the 2nd statement, and that will run before the 3rd statement, that will run before the 4th statement. So in a case where you have 3 assignments this way, this first assignment will run before this assignment, and then this assignment. However, with processes, assignments don't get done until the process suspends or the process ends. In other words, if we didn't have any wait statements, then any assignment we do inside this process will not occur until we reach our end process command. But if we have a wait statement, then whenever you have a wait statement, any assignments that happened before that wait statement will get assigned when you have your wait statement. In other words, when VHDL gets to this point, VHDL will assign a low to SCRN, then it will assign not this to the clock and not this to the clock immediately. In other words, this state will seemingly not exist. So that if I wrote, it will seemingly not exist, and we will hopefully see this in our simulation. So we probably will never want to do this, because you probably want to have a wait statement in between. Otherwise, you might never really see this, or you will never see the effect of this particular command in your simulation. But I'll go ahead and leave it in there so we'll see how things run. So after this occurs, then I'm going to clock the system one more time. And then I want to take these two lines of code once again, and I want to run them a couple of times. Now, to make things a little faster, I'm not going to paste a couple of times. Instead, I'm going to say for I, I'll just create an integer from I in 0 to, let's say, 10. So I'll make this run 10 times, loop. And then I'll now paste in the code I had in there. And after that, I will end loop. Okay, so I hope you see what excuse me. Control, what was that? Control Y. Control, okay. So code is back. I thought I just lost everything. Okay, so I'll just type that last line of code once again. End loop. Okay, so I just want to indent this. Indenting your code makes it easier to read. So it's always good practice to indent your code. Now, what I've done in here is I've created a loop that will occur 10 times. So instead of having to paste this 10 times, I know that it will occur 10 times. I could have instead decided to make this, in fact, I could just come back and make this 100 times, make this 50 times, as the case may be. It makes it a whole lot easier to use. So I would suggest you use a for loop wherever you can. Next, I'll copy this entire line of code, lines of code, and I'll just paste them in once again. This time, what I want to do is set n, and then I'll run my loop a number of times. Okay, so this, in this case, I will take that out. And if I don't need to clock it really in here, let's just take that out as well. Okay, so this is my code. This is my test bench. Remember, the meat and bones of this test bench is the fact that I had a component I brought in, or as many components as I need, I brought them in. Then I specify all my signals in here. I do my port mapping. After all of that, all I'm doing in this process, this entire process, all I'm doing in this process is I am assigning stimulus signals to my inputs, to the various inputs. It's a good idea to apply all possible stimuluses to your inputs. Oh, there's one more thing I did not do. I made my clear active and I never made it inactive. So I need to make it inactive after this wait statement. So I make my clear inactive. I need to do the same thing for my set. Otherwise, after setting or after clearing, it will not get inactive. Okay, so this is, oh, sorry, this should be 1. Same thing here. This should be 1. Okay, I think we're good now. So now we can compile this and test it. So here in ModelSim, I click on this button. Okay, so let me do that once again. So I'm going to dock this window. I'll dock the window once again so that we can see everything that is going on in here. So I could go to compile and click on compile, or on my toolbar, I could click on this button here that says compile. So I'll click on this button here that says compile. It's a lot easier to do that. I want to compile into the library called work. I'll navigate to my folder I'm working with. Now, TFF, I'll go ahead and compile TFF so that I have it inside my work folder. Now, because I came from quarters, TFF will already be in my work folder. If I check my work library rather, TFF will already be in my work library because I came from quarters. If I had just opened ModelSim out of the blues, then I'll have to compile it to make sure it is in my work library. And then TB, my TFF, I'll compile that as well, so that will also be inside my work library. Now let me go ahead and expand my work library. Now in my work library, you can see I have my TFF, and this is the architecture in there. TB, my TFF, and this is the architecture in there. Now it is particularly important to note that, or maybe I should just specify that if I had multiple architectures, you see the various architectures in here. So I could have had a different architecture where I'd have a different process in there, and I could have that separate architecture so you can decide which of the architectures you want to simulate. The particular architecture I want to simulate is this architecture. Well, it's the only existing architecture for my test bench. So I right click on it, simulate. It will open up the simulation environment here within ModelSim, and we're almost done with our simulation. Okay, so it has opened it up here. Now, when it opens it up here, because I have some VHDL files open, this same window is where it does the simulation. If you look over here, you see a tab has opened up called waveform. Click on that, bring up the waveform so that this is clear here. Now, what do you want to view on this waveform? Look at this objects window over here. Select the particular signals you're interested in monitoring. So in this case, I'll select all the signals in there. And for your test bench, many times you're interested in selecting all the signals because you want to see how all of them are behaving. How long do you want to simulate for? That's the run length. You have it over here. I will simulate this for, say, 50 nanoseconds. Now, if you simulate for a very short time, you could always increase that later on. In fact, let's simulate for a short time, and then I'll just show you how you could go on. So we're running this for 10 nanoseconds. Is 10 nanoseconds short? The answer is yes. If you come in here and check, waited for 2 nanoseconds, another 2, another 2, another 2, another 2. So at this point, we've gotten to 10 nanoseconds. So what's the total amount of time that this simulation should run for? Honestly, I don't know, but I'm not going to worry my head too much about that. So I'll go ahead and clean. So I'll pop this out and enlarge it so that we can see the simulation very well. Okay, so enlarged it over here. Now I can click on this button. Sorry, not compile. Where's the run? Okay, so this button over here to run. Click on it. It runs it for 10 nanoseconds. I'll right click on this and say full, just so that you can see it, or you could just scroll through here. Okay, take note that this is 8.4 nanoseconds. Down here, you have 10 nanoseconds. I could click and scroll through and see what is happening. But I'll right click on this and or simply press F on your keyboard and full. So this shows you everything happening full. 10 nanoseconds doesn't show us the entire picture. Let me run this again for another 10 nanoseconds. Notice now it is 20. I could run it a whole number of times. Okay, I just click on this a whole bunch of times. Now it has run 110 nanoseconds. I'll right click again, full. So this shows the entire run length from 0 nanoseconds to 110 nanoseconds. You may not always want to zoom full. You may want to click on this to zoom in some cases. You may want to zoom out specifically. You could zoom out beyond a certain point, but many times if it doesn't run for too long, I zoom full. So we waited for 2 nanoseconds. We flip the clock, then we flip the clock, then we flip the clock, we flip the clock. Here we see our Q, okay, SQ. We see that is flipping, and that is good. Okay, so it is working exactly the way we expect it to work. Then we get to this point, and our clear signal goes active for 4 seconds. So clear signal goes active for 4 seconds. Notice your Q is cleared, and it stays that way until we have your next active clock transition. Now, remember that we had our clock. We flipped our clock twice. Notice that if you come in here, let's even zoom in closer. Sorry, so let's scroll. Okay, where are we? Yeah, this is what we're interested in. This is the region we're interested in. I just clicked in there to put in a cursor. So I'll zoom in a little more. Where is the active point? Now, let me take my cursor away from there. We're looking for it. We're trying to see, did it zoom? Did it flip twice? And I hope you can see that it did not flip twice. Where did my clear signal go active? Okay, this way. So you don't see that flipping and then flipping because, yeah, it happened. Remember, the assignment happens at the wait statement. So when the wait statement occurs is when it's supposed to do all the assignment, and you don't notice that happening over here. So it's not a good idea to assign 2 signals before you wait, and 2 different values to the same signal before you wait. You want to assign things in the right way. Okay, then we continue flipping the clock a couple of times. This is where we used our for loop, and then our set signal goes active. Our output was low before. Here it goes high, and it stays high until your next active clock transition. Okay, so we see our signal works. We see our T flip-flop works exactly the way we wanted it to work. If you want to restart your simulation, you could always click on this button, and that will clear everything you tell it to clear. And it has cleared the entire signal. You could decide to change this run length if you want, and run for whatever time it is you want to run for. Again, we could decide to zoom full and see how as things are. While we're in this environment, let me also mention you could right-click on any signal here. You could decide, for instance, to come to format and change what you want it to be like, or come to radix, change what you want it to be like. Use global setting or specify you want it to be a decimal number, you want it to be a binary number, you want it to be symbolic, you want it to be unsigned, you want it to be hexadecimal. So if we click on hexadecimal, now it is showing as hexadecimal, but hexadecimal and binary effectively are exactly the same thing. So in this case, the radix, you won't notice the radix, the effect of the radix, unless you had, for example, say the signal you are monitoring was an integer. If the signal you are monitoring was an integer, you could decide to now right click on this and make the radix something else. And then you could now view it in a different base, for example, as a hexadecimal or as an unsigned number or as a binary number. And it will show it to you as a binary number. Feel free to play around with this environment and see. I mean, there are several things it can do in here, but we will not cover. This is as far as we'll go in this video. When you're done, you could always come to simulate and say end simulation. That will close the sim. Are you sure you want to simulate end simulation? The answer is yes. Now that will close the simulation environment. It doesn't close. Okay, sorry about that. Let me minimize this window. It doesn't close. Okay, that's quarters. Where is ModelSim? ModelSim for some reason is hiding. Okay, so that is ModelSim. Okay, so it doesn't close the ModelSim environment, but it closes the simulation environment itself. Okay, so it closes the simulation environment, not the ModelSim environment. We can always right click on this and click on simulate, and that opens the simulation environment one more time. One final point to note. If you look at this bottom window over here, you see that it shows a couple of things in here. Now, one thing you should take note of is that you could actually, instead of clicking on this and clicking on buttons, you could simply type commands. And if you type in commands, if you look specifically at some particular commands you have over here, okay, let's just go down to the very bottom. Look at this command you have over here, vsim walk.tb, so and so. So this calls the simulator and starts up the simulator, and it tells it, look inside the work folder, look for tb_my_tff and run the particular architecture called test_my_tff, and that will run it over here. Okay. The command run is used for running the simulation. Command restart is used for restarting the simulation. Okay. So you could do a whole bunch of things. This added waves to your simulation. So instead of doing these things using the GUI, you could as well type in commands and that will work. So just to mention that that is possible. That will be it for this video. In the next video, we'll actually now create a toggle, a ripple counter, which is an up counter and a down counter. A ripple counter will be created in the next video. Thank you.